In this section of Unit 2.4, we're going to look at the applications of the first law of thermodynamics. And the first application we're going to look at is the refrigerator, otherwise known as a heat pump. Okay, so have you ever wondered how a refrigerator actually works? On the back of the refrigerator, there are coils, and the coils radiate heat. So the refrigerator is actually taking heat from the interior and pumping it out to the exterior. That's why we call it a heat pump. And it does this through the use of something called a compressor. A compressor does exactly what it sounds like. The more science I study, the more I realize some of these names are not very creative, but that's good. It helps me remember. The compressor simply compresses gas. So here's what happens. We'll start here at step A. And step A is just before, I'll change my color here. Step A is just before we get to the compressor. So we've got fluid, we've got a volatile fluid. That means it's easy to evaporate. We've got a volatile fluid in this tube. And when it gets to the compressor, it gets rapidly compressed. So here's a visual of the compressor. It's going to be rapidly compressed. Now, what happens when we rapidly compress a gas? The temperature increases. And so the blue going to red is trying to show that. Again, here in this picture of the refrigerator, in the compressor, the temperature is going to increase as the compressor does its work. So the compressor is doing work on the gas to compress it. Okay, then what happens? We've got this hot gas going through the tube, and this is what that looks like. There's hot gas coming through these condenser coils, and they actually, to condense means to go from gas to liquid. Okay, so while they're going through these coils, they radiate heat, and the gas turns to liquid. Okay, in this diagram, you can see there's condensation. The gas is turning into liquid. And it's important that it turns into liquid by the time it gets to this expansion device. Because what the expansion device is, it's like an aerosol can. It has an adiabatic, there's an adiabatic expansion. In other words, there's a, well, as my kids would say, we like Ready Whip in a can. You know that sound of Ready Whip in a can? Psh, that's adiabatic. Psh. So you have gas expanding rapidly. And when the gas expands rapidly, which happens here, it's going to cool down. In fact, it cools down so much that it cools down to be colder than what's inside the refrigerator compartment. And it cools down to be colder than the refrigerator compartment so that it picks up heat from the refrigerator compartment and then carries that back to the compressor, and the cycle begins over again. So I have those steps written out here as well. But again, it's a 4-step cycle to move heat around. So to summarize the 4 steps, step A, the heat is absorbed from inside the refrigerator. The gas is compressed in the compressor, which warms the gas up and turns it into a liquid. The refrigerant cools, the gas warms up, then it turns into a liquid when it cools, when it releases heat to the surroundings. That's on this radiation portion. And then finally, there's an adiabatic expansion of the gas, which lowers its temperature to be colder than the inside of the refrigerator. So in this case, mechanical work is used to move or transfer heat. Okay, The next application of thermodynamics that we want to look at is a heat engine. And if you haven't looked at it already, please watch the video I linked before this one with Bill Nye, who shows something called a Stirling engine. But a Stirling engine has a cycle as well. So the first part of the cycle is that we need a heat source or a heat collector. It could be solar, it could be a candle, it could be coal, it could be gas, but we need a heat source. Then what we do is we heat up gas and we use that gas to turn a turbine. So here we are using heat to do work. So this is the reverse of the heat pump, where we were using work to move heat around. Anyway, turning a turbine can generate electricity, which is actually the focus of units 3, 4, and 5. When we're done turning the turbine, or when the gas goes through the engine, then we need to cool it down before we can use it again. So there's a heat radiator. This is also sometimes called a heat sink, a place for the heat to go. Some places, like power plants, for a heat sink, they'll use a water source, like Lake Monona is a heat sink for MG&E, and you'll see parts of Lake Monona that do not freeze because of that. Anyway, the cool gas is returned to the heat collector, and the cycle repeats. So this would be a closed loop of gas. The net work done, ideally, should be, oopsie, problems with my automation here. The net work should be the difference between the heat collector, which we're going to call QH, or the hot part, and the heat sink, QC. Whatever happens between these two things, between the heat collector and the heat sink, the energy difference between those two should be the work done by the engine itself. And it's also helpful to know that QH must be bigger than QC. It has to be for this whole thing to work. But another thing we need to remember, though, is that inevitably through all of this process, we are going to lose some heat to the surroundings. It's not going to be perfect. There's going to be friction. There's going to be other irreversible processes, and the universe tends toward disorder. So that's the second law of thermodynamics, is that this will never be 100% efficient. Partly because QC can never be zero. 0 Kelvin would be impossible to reach. Okay, what we can do is we can compute the efficiency of an engine by taking the net work over the heat that we put in. Remember that the net work is the heat we put in minus the heat we get out. And if we rearrange this equation, we get 1 minus QC over QH. That's how we can compute the efficiency. So let's try an example problem. Find the efficiency of a gasoline engine that, during one cycle, receives 204.5 joules of energy from combustion. Okay, so this is a different way of saying QH, the heat received or gotten from the burning or the combustion, and loses 153.3 joules of heat to the exhaust. So the exhaust is the heat sink, or the cold, sometimes called the cold reservoir, even though it might not actually be cold to us. So the efficiency is going to be 1 minus QC over QH, 1 minus 153.3 over 204.5, and I get 25% efficient. Okay, now, since we know that Kelvin is directly proportional to internal energy and heat, we can also rewrite this equation in terms of temperature. It's just really key that the temperature is in Kelvin when we solve this. So find the efficiency of an engine that has a heat source at 400 degrees Celsius. So I'd want to add 273. And an exhaust at 90 degrees Celsius. So that would be 363. So I could do the same thing. Oops. Okay, and what do I get here? I get 46% efficient. Again, to get perfect efficiency, to get 100% efficiency, this would need to be 0, and that can't happen. Okay, finally, we want to take a minute to talk about something called the Carnot Cycle. And Carnot basically, because of the second law of thermodynamics, which says that some processes are irreversible and that the universe increases in disorder, says that basically not all processes that are possible according to the law of conservation of energy can be realized in nature. And the scientist named Carnot tells us that there can be no perfect heat engines. Heat is always lost somewhere to the surroundings. So a theoretical Carnot engine tells us what the maximum possible efficiency can be for an engine, and it's the same formula that we just went through. That's the best possible efficiency that we could get. But in reality, we usually lose even more energy to friction. So here's an animation of the 4-step Carnot cycle. And let's see. We'll start here. Okay, so there's heat and then an expansion. You can see the temperature going down, and then an isothermal compression, and then an adiabatic or rapid compression. These are the 4 steps to the cycle. Now, what you're not seeing here is that for the adiabatic expansion, there has to be some kind of combustion. And in like a combustion engine, like in a gasoline engine, there's actually a little explosion that happens inside of the piston. Gas is sprayed into the piston and a little mini explosion happens. So there is the Carnot cycle. So going back here, the 4 steps, let's see. The 4 steps would be, we've got an isothermal expansion. That's part A. Remember the shape of an isothermal graph. The heat that is absorbed goes into work done by the gas. So here this hot gas is expanding and pushing out the piston. And then there's an adiabatic expansion, or rapid expansion, and the piston does work and cools down at the same time. Then the piston compresses. And why does the piston compress? So in this picture, what happens is this is something called a flywheel. This wheel on the right is heavy and it has conservation of momentum. It wants to keep rotating once it starts going. So that's why the piston will compress, because of that conservation of momentum. And then we have an adiabatic compression. Again, the momentum helps do that, or conservation of angular momentum helps do that, and work is done on the gas, causing a temperature increase. Again, this is an idealized cycle that's intended to show the 4 steps of an engine. And again, Carnot, who came up with this, also came up with this efficiency equation. All right. finally, on the last page here, I just have some vocabulary that I've talked about throughout the unit, and it would be good to make sure that you understood and knew what all of these words mean. Heat sink, heat source, entropy, the first law of thermo, the second law of thermo, heat engine, refrigerator, heat pump, and reversible and irreversible processes.